I got started on this on a completely different question, which has nothing to do with the talk, but the subject, but it's a nice introduction. I was approached by a student in quantum mechanics who had this question. What happens if you shoot a pion beam through a potential barrier? We know what happens, that part of it is reflected and part of it goes through. But a pion is an unstable particle, and it decays. What is the probability that it decays while it's going through the barrier? Because we know that a relativistic particle has a time dilation, and the decay rate is slower when it's moving, when it has a high momentum. But what happens if it has an imaginary momentum? And so we looked into this problem, and then after we solved it, we said, well, suppose we now put a magnetic field in the barrier. And then it got complicated. And at that point, I started to think differently. I said, hey, this is interesting, but why do we need the barrier? Suppose you have an electron just going through a slab where there's a magnetic field, and you end up with all these problems that David Gross talked about of is the vector potential real or just a mathematical device? Is there redundance and all that? So as Murray Peskin has pointed out, I see this thing works. The Coulomb field of the electron enters the magnetic field, and there's momentum and angular momentum in the cross fields, and these are described by the use of the vector potential at the position of the electron. But the pointing vector of the crossed fields goes far beyond the electron's position. So somehow the vector potential at the electron's position knows about the pointing vector far away. This is a question. And when I showed my example to Dave Jackson, he didn't believe it, and he had to calculate it himself to see that it was right. And then he asked me to allow this example in the new edition of his books, Classical Electrodynamics. She's supposed to. Sorry. Oh, what? What is this?
Yeah. Just press cancel.
Cancel. Okay.
And just roll.
Oh, okay. So, where are we now? I want it back here. So, I didn't draw the picture, but I think that it's simple enough so you'll just see it. We have an electron coming in. There's these lines are supposed to be straight. There's a magnetic field perpendicular from z equals minus a to z equals plus a. And we all know what happens. The electron goes to the magnetic field, there's a Lorentz force, and it gets deflected. And this is something that any student can calculate and get the right answer. But then when you start thinking about it, you immediately think of it with some kind of theoretical picture. And there you see right away that the magnetic field is in this direction. It's Hamiltonian, the interaction, everything is invariant under translations in the y direction. So the momentum in the y direction has to be conserved. But it manifestly is not conserved in motion of the electron, because here it has the momentum, y component of momentum is 0, and there it is finite. So where does this extra momentum come from? And the point is that it's easy to resolve this paradox, but the point is you find that there are two ways of doing it, which seem to be completely different, but they must be related. One is that it is locally in the vector potential at the position of the electron. And that, of course, you calculate it, and it gives you the right answer. The other one is to say, well, when the electron is outside, its field still goes through the magnetic field in this slab, and therefore there's a pointing vector, and there is a momentum. And you can calculate the momentum by integrating this pointing vector over the whole slab from x and y going from minus infinity to plus infinity, and you come out with the same answer. But somehow, this depends on knowing the pointing vector all the way out to infinity. It seems to be completely non-local. And so there is the question of how the local value of the vector potential is and that is really the problem, which asks, if you want to say the vector potential is some mathematical device, you can get everything that will be measured without using the vector potential. But in order to conserve momentum, you have to include fields that go out to infinity. And that somehow doesn't sound reasonable. And so the question is, using the vector potential at the point of the electron gives you a local description of everything you need. But if you don't want to use the vector potential, you can do it too, but now you have to have fields going through the slab out to infinity. And actually, well, I think that really says it all. I mean, you can calculate it very easily. The Lorentz force on the electron gives you a potential, gives you a momentum change in the y direction, which is just the usual of V cross B, and it ends up by just giving you essentially the flux through the slab from minus A to plus A. If you now put at the change in the vector potential going through the slab, well, you do the same kind of integral, and you get the same answer. I mean, with the opposite sign. I'm not sure. I know that they have to be opposite sign, but if I've made mistakes in signs in this calculation, I made an even number, and I get the right answer. And then, of course, there's a change in the Poynting vector, and that's simply EXBY integrated over everything. It's a more complicated integral, but it works and gives you the right answer. So that is essentially the point I'm trying to make, that all of these questions that David Gross and others have asked can be seen in this simple model. And if you can understand these various connections in this simple model, you can learn a lot about more general things. I think that's it.
Please speak loudly.
This system has also quantum analog, namely scattering, quantum scattering from a magnetic stream.
I ended up just doing the classical thing because there is enough things to be understood in the classical problem.
Please,
Excuse me.
loudly. We will ask not to use the microphone.
When you said the new edition of Jackson, is it the third edition or is there
It's the one that has just come out. The last one that has come out.
Okay, thank you.
It's an exercise. It's somewhere. I mean, where he talks about the momentum in the field, and he didn't believe when I first said it that you could actually calculate the momentum in the field, and it would give you the right answer for a simple problem like this.
Thank you.